My dear students of class 10, I am Shantipriya sir, going to discuss about chapter 10, light, reflection and refraction of physics, right? Now, at first we know the refraction through a parallel glass slab. Refraction through a parallel glass slab. Let AB and CD AB and CD be the two parallel sides of a glass slab ABDC, and incident ray PQ, it is PQ, incident at Q on the reflecting on the surface AB. It is normal. In next, right? After reflection at Q, since the first medium is air and it is a glass, material is glass, and also the emergent media air, its refractive index N1 equal to 1 approximately, its refractive index N2 equal to N, say, and this is also here, that is N1, refractive index being N1 equal to 1 approx. Hence, light rays PQ refracted from rarer medium, this is rarer medium to denser medium, this is also rarer medium. Hence, reflected ray bends towards the normal. This is angle of incidence I1, this is angle of reflection R1. It is bends, the reflected ray bends towards the normal, that is R1 less than I1, angle of reflection less than angle of incidence. Now, here also we draw a normal. Now, since light rays are refracted at the face CD at point R, this is the point R, and the light rays coming from denser medium are reflected at the rarer medium, hence the reflected ray bends away from the normal at R on the face CD, RS, right? Here, this is angle of refraction due to reflection at Q, and here obviously it will be the R1, since this is parallel to this, that is two normals are parallel because two surfaces are parallel to each other. Here both are perpendicular to the parallel slabs faces. Hence R1, this is the alternate interior angle. Hence these are equal. It is angle of emergent I2, right? Here we see that light ray, incident light ray is directed If the glass slab is absent, will be in this way. In this way. Incident in this way. That is, direction of incident ray and the direction of emergent ray are parallel to each other actually. We can prove it. Now, if we draw a perpendicular on this line, right, then this is the lateral displacement or lateral shift. It is also, if we extend produce it, the emergent ray in the backward direction, then we draw perpendicular from Q, will also be the lateral displacement, distance between the direction of the incident ray and the direction of emergent ray. Right. We use Snell's law due to refraction at Q. We use Snell's law due to refraction of light at Q. We get refractive index into sine of the angle of incidence, that is N1 sine I1 equal to, here refractive index N2 and the angle of reflection R1 N2 sine R1 and this is equation number 1, and due to refraction at R, we get by using both by using Snell's law of refraction of light, by using Snell's law, we get by using Snell's law, that is N2 sine R1, N2, that is in this medium, refractive index of this medium, glass medium, into N2 into sine of angle of incidence here due to the phase CD R1 equal to, here the refractive index being N1 sine R1 sine I2, right? These are the two equations. Now for air we use N1 equal to 1, and for the glass, material of the glass, refractive index N2 equal to N, right? But for air N1 equal to 1, and for glass its refractive index will be N2 equal to N same. By using these in the equations 1 and 2, we get N1 equal to 1, here N1 equal to 1 here, N1 equal to 1 here, right? 1 into, from the first equation, 1 into sine I1 equal to N2 means N, right? N into sine R1, sine R1, and this is from equation 1, from equation 1, and from equation 2, N2 equal to N into sine R1, equal to N1 means 1 for here, 1 into sin I2. Sin I2, right? From these equations, this is An into sin R1, this is also An into sin R1. By comparing these two equations, we have sin I1 equal to sin I2. It is equation number 3 and this is equation number 4. By comparing equations number 3 and 4, we get n sin R1 in the first equation, in the second equation n sin R2 equal to 1 into sin I2 and equal to 1 into sin R2. Hence, these are equal. By comparing equations 3 and 4, we get sin I1 equal to sin I2. Sin I1 equal to sin I2. That means I1 equal to I2, which implies that I1 equal to I2 means PQ parallel to RS. That is, there is no deviation actually due to refraction at Q and R. Only the lateral shift or lateral displacement occur, which is denoted by delta, right? Lateral shift. What do you know lateral shift, right? Noted in your exercise book. Hence, since I1 equal to I2, it is obtained I1 equal to I2. Hence, the incident ray PQ and emergent ray RS are parallel to each other. Hence, no deviation occurs, right? Only lateral shift or lateral displacement. Lateral shift or lateral displacement occurs, right? Now, what do you mean by lateral shift or lateral displacement? Copy in your exercise book that the normal distance, that is perpendicular distance between the direction of incident ray, and the emergent ray is called lateral shift or lateral displacement. Define it again. The lateral shift or lateral displacement is defined as the perpendicular distance or normal distance between the direction of incident ray and the direction of emergent ray. Right? Remember it. Now, after calculation, we have lateral shift or lateral displacement. Lateral shift equal to T sine I1, right? Remember it, T sine I1, T sine I1 into 1 minus cos I1 by square root of n square minus sine square I1. Lateral shift may be written as d or delta. Lateral shift equal to T sine I1, that is thickness, T be the thickness of the glass slab, rectangular glass slab. I1 be the angle of incidence, right? N square. N means the refractive index of the material of the glass slab, right? Hence, we see that the lateral shift due to refraction of light through a parallel glass slab or rectangular glass slab depends upon the thickness of the glass slab, rectangular glass slab, T. Angle of incidence depends upon the angle of incidence, I1 also, and depends upon the refractive index of the material of the rectangular glass slab, that is glass, right? Remember it. Now we see that if normal incidents occur, what will happen? It is a medium, say medium 1, this is medium 2. Here a normal incident occur. The incident ray AOB will be the refracted ray. This is the M1, M2 or S1, S2 refracting surface, right? Here we see that angle of incidence I equal to 0. I equal to 0. R will also be 0. We see how. And this is medium 1, this is medium 2. From Snell's law, that is second law of refraction of light, this is this medium N1, this is N2, refractive indices, right? N1 sine I equal to N2 sine R, that is refractive index of the first medium into angle of incidence on the first medium, its sine of angle of incidence on the first medium is equal to the refractive index of the second medium multiplied by the angle of refraction in the second medium, that is refractive medium, right? Now, therefore, sine I equal to N2 by N1 sine I, right? N2 by N1, or it can, what do you mean by this? This is the absolute refractive index of the second medium, and this is the absolute refractive index of the first medium. N2 be the refractive index, absolute refractive index of the second medium, and N1 be the absolute refractive index of the first medium, right? And this is also N21. That is refractive index, relative refractive index of the medium 2 with respect to medium 1. Now, if I equal to 0, that is for normal incidence, that is for normal angle between the incident ray and normal at the point O on the refracted ray being 0 for normal incidence. Then sine I, that is sine 0 degree, equal to I equal to 0 degree, equal to n21 or n2 by n1 sin r, that is, this makes 0. That means 0 equal to n2 by n1 or n1 to n2 by n1 sin r. But n2 by n1 cannot be negative, cannot be 0. Therefore, sin r equal to 0 since n2 by n1 or n21 not equal to 0. Therefore, sin r, that means sin, that is r equal to 0, sin 0 degree 0, r equal to 0, 0. That is, for normal incidence, angle of incidence and angle of reflection are both 0. Now, we know about some sign conventions we adopted, right? For deriving different formula due to reflection through spherical mirror or through reflection or refraction through spherical lenses. We first adopt some sign convention for measuring distances. This sign convention we adopt will be the new Cartesian sign convention. New Cartesian sign convention, right? New Cartesian sign convention are used. We use new Cartesian sign convention. We know about it. For deriving different formula due to relevant formula due to reflection through spherical mirror or refraction through spherical lenses, we first adopt some sign convention for measuring different distances. And heights also, distances, different distances, right? At first, some assumptions are taken here before using these new Cartesian sign conventions. The object will be taken as point object, which is placed on the principal axis, and obviously, hence the image will also be a point like image. Remember it. Now, in the case of spherical mirror, we measure all distances from pole of the mirror, of the respective mirror, right? During measure, and in the case of reflection, we use optical center of the lens as origin from which all distances are to be measured. Right? Remember, we take only the reflecting mirror, spherical mirror, reflecting spherical mirror, which P be the pole of the mirror, and this is the otherwise x prime, yeah, like P be the pole, and this is the first principal focus F. This is the center of curvature C, right? Here, object is placed beyond C, relatively, right? When we measure the distance, this is the direction of incident ray, direction of incident ray. At first, we use the pole as the origin, that is, distance is measured from the pole due to a spherical mirror, and from the optical center due to reflection from a spherical lens. If we go towards the incident ray, find distance measured from P. If the distances measured from P is along the direction of incident ray, then it will be the positive. This distance will be positive. And if we go opposite to the direction of incident ray, find measured from pole, then it will be the negative. Remember it. Right? In this case, we see that it is the focal length, and this is the radius of curvature R. If we measure the focal length for a concave mirror, then when we go from P to F, that is opposite to the direction of incident ray, hence it will be positive here, will be negative here, opposite to the direction of negative here. This also negative here. That is, F and R both are negative in the case of concave mirror. Here we see that. If the object is placed above the principal axis, then this the positive. This will be the positive. And if below the its image, let AB, A dash, B dash, A dash, B dash, then it will be the negative, since the height is situated below the principal axis. Right? In this case, you see that the erect object, we see virtual image. For the case of virtual image will be behind the mirror, and hence we go when this distance measured, image distance want to measure from pole, its direction will be along the direction of incident ray, and hence it is positive. That is, for virtual image, means erect and upright image, the distance, image distance will be positive. Obviously, for the real image of the object, of an object, will be the negative, because we go and measure from P opposite to the direction of incident ray. Remember it. Right? Magnification, the same case. Magnification for a virtual image will be positive, and magnification for a real image will be negative. That is, magnification for virtual image or erect image will be positive, and magnification for an object, right, which is real, means inverted, will be negative. What will be the magnification? Magnification is the height of the image by height of the object, or this will be a negative sign will be put, or it will be the minus v upon u, that is image distance by object distance, right? Now in the next class we use the refraction of light through a lens.